Problem number 2 on page 196. We're asked to solve Laplace's equation on the exterior of a disk of radius rho. And here's the picture. We're looking at a disk-like region of radius rho, and we want to solve the boundary value problem on the exterior. So we have Laplace's equation in polar coordinates. R is greater than rho, and rho is a positive number. And here we have our periodic boundary conditions. We see that the negative x-axis is in part of the domain, and so we're going to be forced to require periodic boundary conditions in theta. So the first thing we're going to do is separate variables. We'll write u of r and theta equals r of r times f of theta. I write f of theta rather than capital theta of theta, as it's kind of difficult to write that. Substitute into our differential equation after multiplying through by r squared, so we'll have r squared r double prime f plus r prime f plus r f double prime equals 0. This is a function of, well, we have to, first divide by rf and cancel what we can. So here we cancel the r's, here's the f's and the f's. And now it's true that this is a function of r alone, and this piece is a function of theta alone. And so we're going to write it this way: r squared r double prime plus r prime over capital R equals minus f double prime over f. And since both sides involve different variables, we know both sides must be constant, and to get our standard equation in theta, we're going to set this equal to plus lambda. So let me tabulate our two differential equations here. The theta equation is our standard f double prime plus lambda f equals 0, and our r equation is a Cauchy-Euler equation, r prime, and this will be minus lambda r equals 0. We're going to require that we have periodic boundary conditions in theta, so we want to write that down. So f of minus pi equals f at pi, and f prime at minus pi equals f prime at pi. And for the r equation, let's point out that we were going to require that r and r prime bounded as r goes to infinity. So here's our eigenvalue equation, and this is one of our standard equations. It's tabulated inside the front jacket of our book, and we know lambda equals 0 is an eigenvalue, and its eigenfunction is 1, or any non-zero multiple of 1, and the eigenvalues for positive n are n squared, and the f sub n's, there are, I'm going to put alpha sub n cosine n theta plus beta sub n sine n theta. So we have two different forms for the eigenfunctions. And now that we know the lambdas, we can solve the r equation. And in fact, if we make the assumption that r of r is equal to r to the p, the characteristic equation is p squared minus lambda equals 0, or p equals plus or minus the square root of lambda. When lambda equals 0, let's look at lambda 0 equals 0, we get a repeated root, and our r equation is r is equal to a0 plus b0 log of r. And when lambda n is n squared for positive n, we'll call this one r sub 0, we have r sub n is equal to an r to the n plus bn r to the minus n. So there are the two solutions depending on what lambda is. Let's apply our bounded conditions now. We know that as r goes to infinity, this piece goes to infinity, and hence we're going to have to choose the a's here to be 0. This piece goes to 0. As r goes to infinity, we're okay. As r goes to infinity, a0 is just a constant, but we know that this piece goes to infinity as well, and so we're going to again have to choose b0 to be 0. So now we have the solution of the eigenvalue problem and the r equation, and we can construct our general solution. The general solution is going to be u of r and theta is equal to r0 times f0 plus summation n starting at 1 of rn fn, and I want to write that out. So let's see, r0 is a constant and f0 is 1, so we'll just put that to be a0. And then plus our summation starting at n equals 1 to infinity. So we'll have b sub n r to the minus n from the r equation, and then from the theta equation we have alpha sub n cosine n theta plus beta sub n sine n theta. What I want to do next is take this and these two together and define their product to be, I'll call it capital A sub n. And the product of b sub n with beta sub n, I'll call that capital B sub n. So finally we can write down the general solution. Let me write it on the next page. So our general solution will be u of r and theta equals a0, and you know I'm going to write this as a0 over 2, and we know why because of our formulas for the coefficients. So n equals 1 to infinity, r to the minus n, an cosine n theta plus bn sine n theta. Here's our general solution that satisfies the periodic boundary conditions and is bounded at infinity. The last thing to do is to apply our boundary condition that when we set r equal to rho, that the result should reduce to our given function f of theta on the interval minus pi to pi. So we'll set r equal to rho up here, and our formula then will be f of theta equals a0 over 2 plus summation starting at 1, and I'm going to write this as rho to the minus n an cosine n theta plus rho to the minus n bn sine n theta. And we recognize this as a full Fourier series for the function f of theta on the interval minus pi to pi. And so in fact we know the formulas now. A0 is given by 1 over pi, integral minus pi to pi, f of theta d theta. And solving for this coefficient, we'll write rho to the minus n an equals 1 over pi, integral minus pi to pi, f of theta cosine n theta d theta. And we want to solve for a sub n and write this as a sub n is, well, it could be 1 over rho to the minus n. Let's write it as rho to the plus n over pi, integral minus pi to pi, f of theta cosine n theta d theta. And similarly, we'll immediately get a similar formula for b sub n. It'll be rho to the n over pi, integral minus pi to pi, f of theta, this time with the sign, sine n theta d theta. So at the top of the page we have the general solution for the boundary value problem. When we apply the initial condition that the solution reduced to a given function f of theta on the boundary, then we get this full Fourier series for the function f of theta, and here are the formulas for the coefficients.